Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So, good morning, students. Happy Makar Sankranti to you all. So, if you remember in our previous class, we have studied about a structural representation of organic compounds. A structural representation is what way one can represent organic compounds, or what way one can write it on the paper, so that one can understand of what this is, this particular organic compound. So, to do that, we particularly follow three different representations, and one is to write complete structural formula, and that writing complete structural formula, we also call that a structural formula as a Lewis structure or dot structure. And this Lewis structure and dot structures, we know we show all the electrons that are there that are involved in chemical bonding. So two electrons, if they are there, they are shared between two different atoms. We know they are bond pairs, and those bond pairs we can also represent as the dash lines. So if there is a single bond, one can write one dash, double bond means two dashes, means four electrons are involved there, and if the six electrons are involved there, means each atom share three electrons, there will be triple bond. So three dash lines one can use, and so that will be dash structure, and that one way one can write complete structural formula as shown in this case here. So ethane we know, this is ethene, these things I have already explained. Then we move to condensed structural formula. What is the condensed structural formula? If instead of writing these all the bonds, showing all the bonds, you just write different groups that are attached to carbon atom, and let the reader understand what else valency and other things that is there in that compound. So if this one can write CH3 1 dash CH3. This will also be a condensed formula, or CH3 CH3. So one can write this ethane as CH3 CH3, that will be condensed structural formula. Similarly, I can write this CH2 double bond CH2 or CH2 double dash CH2, and like here, or I may not write even this double bond or double dash. I may not represent it with this. CH2 CH2 will also be a condensed structural formula for ethene. In this case, one here it was CH3 CH3, here CH2 CH2. This will be CH. So in this case, the reader has to understand that there is a single bond between two carbon atoms in CH3 CH3. There is a double bond between two carbon atoms in ethene, and there is triple bond between two carbon atoms in ethine. And how will we understand this? Because we know the carbon has a tetravalency, it has tetracovalency, and four valencies of carbon should be completed. Since in this compound one carbon is associated to one hydrogen atom, it means its three valency is still incomplete, and that three valency must have come from the another carbon atom. And this way one can understand there is a triple bond, even if it is not shown there. And this understanding is already there. One understand, one expect that a student or a teacher or anyone who is going to study organic chemistry or who is reading organic chemistry, he or she must be having this much sense that carbon has four valency and its valencies must be completed from because of the different atoms that are linked to the carbon atom, and all the four valencies should be completed, and that is why here what we two hydrogen atoms attached to each carbon atom. So CH2, so two valencies that were left, and that must be satisfied by another carbon atom. So there is a double bond, even if it is shown as CH2 CH2. In this case, one understand very easily three hydrogen atoms to one carbon. So three valency completed, one valency is still not shown, and that valency has actually been satisfied by from the carbon atom. So there should be a single bond between two carbon atoms. Then we go to bond line structural representation. Bond line structural representation, what we see, we do not show any carbon and hydrogen atoms. Usually, we carbon and hydrogen atoms we do not show. Instead of them, we write zigzag lines, and based on those zigzag lines, one has to understand where the carbon atoms should be at the each end or bend. Wherever end or bend occurs, the carbon atom is there, and if based on whatever the bond that is shown, one can also find out what would be the number of hydrogen atoms associated to that carbon. So what if I come to here this end, this is a carbon atom, this is also carbon atom, here also carbon, here also carbon. these carbon atoms which are at the ends, if there is no other group, it should be CH3 because this carbon atom has only one bond with this carbon atom. So three valencies of carbon is not shown, and that three valencies must be completed because of hydrogen. So it is CH3 you see here. Here two bonds of carbon are shown. This carbon, it means two hydrogen atoms should be linked to this carbon atom, the CH2. So this will also be CH2, this will be CH3. What another important point that we have to take care of is the heteroatoms. Whenever heteroatoms occur, we show those heteroatoms even in the bond line structural formula. For example, you see here OH group is shown. Even if it is CHO, that CHO group will be shown, the functional group will be shown. And the double and triple bond, whenever it occurs, we also show the double and triple bonds in the bond line structural formula. Whenever the double bond is there, we show these zigzag lines, but in the case of triple bond, we may not need to show zigzag lines just based on the triple bonds, because triple bonds, we know both the atoms that carbon atoms are sp3 hybridized at the triple bond being center, and those groups different bond angles will be 180 degrees. So this, it should be an straight line, and that straight line, if I do not know where, like here in this case, there is a carbon atom, here also there is a carbon atom. So this carbon atom, there is a carbon atom, there is a carbon atom, this heteroatom OH is shown here. So what are the heteroatoms? Again, I'll explain. Other than carbon and hydrogen, whatever the atoms that are there in an organic compound, we call such atoms as heteroatom. And these atoms we know are mostly non-metallic elements. For example, we know halogens, chlorine, bromine, iodine, oxygen, sulfur. Similarly, phosphorus, nitrogen, these are heteroatoms that we see in organic compounds. These are mostly non-metals or non-metallic elements other than noble gases. Means highly electronegative elements. So what we see, so heteroatoms we saw, and based on that one can find out what will be the structure of this compound. Cyclopropane means this CH2, CH2, CH2. These things I have already explained. Another example, I'll just explain here. This one, like this, 1, 2, 3, 4, 5, 6, 7, 8. This compound, 3 methyl octane, 3 methyl will have the third position. How will this name comes? This is IUPAC nomenclature. We will see later on how one can name organic compounds based on the IUPAC nomenclature. So 8 of, carbon atoms are there. To write bond line structural formula, will write make zigzag lines, and these zigzag lines should have total ends and all the bends. Their number should be 8 to represent 8 carbon atoms. So like here, 1, 2, 3, 4, 5, 6, 7, 8. So ends, 2 ends, and 6 bends are here. So total number is 8. So 8 carbon atoms will be there with the hydrogen atoms. And what we see, 1, 2, 3, at third carbon there is another methyl group, one CH3 group. So that CH3 group, one CH3 one can write here. And so a rest of the hydrogens and other things we will have to make understanding based on the valency of this carbon atom. And that this is what we call the bond line structural formula for this chemical compound, this organic compound. Let us, and these things, the examples we have already seen. Let us now move to 3D representation of organic compounds, means three-dimensional representation of organic compound. First of all, why we need three-dimensional representation of organic compound? So what we know, in organic compounds, carbon atoms can have sp3 hybridization, sp2 hybridization, and sp hybridization. If carbon atom has sp hybridization, the shape will be linear, and that we can show, we can represent very easily on the paper. If it is sp3 hybridized, that will also be a planar shape, and planar shape trigonal planar geometry will be there for the carbon atoms. And if all the carbon atoms are on one plane, one can represent that also on the plane of the paper. But if the carbon atom, or one or more than one carbon atom, have sp3 hybridization, it means the geometry of that carbon atom will be tetrahedral. And tetrahedral geometry means the three-dimensional geometry. And in the three-dimensional geometry, some of the atoms will be out of the plane. And how will you represent those atoms which are going out of the plane? So in such a case, if you remember tetrahedral geometry, three atoms two atoms, two terminal atoms, and one central atom. They come, or any three atoms, not only this, any three atoms are on the one plane. Even three terminal atoms, if you look at the models, they will be on one plane. So such there will be four such planes. Another plane would be like central atom. You consider central atom and any two terminal atoms. So in the case of methane, if you look at this central atom and two terminal atoms, any two terminal atoms, we can put them on one plane. Or if you put this molecule in other way on the simple plane, this hydrogen, this hydrogen, this hydrogen, these will be on the one plane. Similarly, this hydrogen, this hydrogen, this hydrogen makes one plane. This hydrogen, this hydrogen, this hydrogen makes one plane. This hydrogen, this hydrogen, this hydrogen makes. So four planes will be there. Another plane will be this carbon atom, and these two hydrogen atoms will also make a plane. This carbon and these two hydrogens also make plane. This carbon, this will also make a plane. So what can we do? We can put three atoms to in 3D representation. A trick we find out, we derived one trick, one method by which one can actually show these compounds as if they are in the the three-dimensional structure, and that we call the wedge structure. Wedge structure, there we use solid wedge and dashed wedge. So solid wedge and dashed wedge we use, and these wedge structure, wedged lines we use to show the bonds which are out of the plane, which are not on the plane of the paper or plane of the screen. So, for example, as I said, a tetrahedral geometry, if a molecule has a tetrahedral geometry, one can, including that central atom and two terminal atoms, one can put them on a plane of the paper. So, suppose in this case, in the case of methane, this carbon atom, this hydrogen atoms, I can put them one plane, and the two bonds, one I can see the normal lines. So, these are the normal lines that we have seen that we use. With the normal lines, it means these three atoms are on one plane. So these planes, these two bonds are on the plane of the paper or the plane of the screen. Now there will be two more bonds, two more extra CH bonds, and those CH bonds, one CH bond will be protruding towards the observer or towards the viewer or towards the writer, and one will go away of the observer. And these bonds, actually these two bonds, we show them with the wedges, the structure, and the solid wedge we use for the bonds which is towards the observer, and this bond is towards the observers, these lines, and if this bond, this CH bond is towards me or towards you, when you see your screen, it means this should be represented with the solid ways, and there will be another bond which will go away from us, and that bond, that the bond that has gone away from us, will show that with a dashed ways. There is another point that one should remember is the broad end of this wedge should lie in which direction? So this broad end of this wedge should always lie towards the observer. Like it, suppose in this representation, this CH group, H group is towards me, and if this H group is towards me, so the broad end of this wedge should be at the hydrogen atoms, because hydrogen atom is towards me, it is nearer to me than the carbon atom, so that this broad edge should be at the hydrogen atom. So the direction of the solid wedge will be like this. In the case of this bond, this should be a dashed wedge, and the case of this bond, the broad end should be at the carbon, because now the carbon atom is nearer to me than the hydrogen atom. So this hydrogen atom is away, this carbon atom is on the plane, and this hydrogen atom is into the plane. So it has gone away, it is away from us. So this should be the pointed end should be at the hydrogen atom, and the broad end of this wedge should be at the carbon. So this is one thing that one should understand. These are the important points. So a three-dimensional structure of organic molecules can be represented on paper by using certain conventions, and this convention is one of the conventions. A solid wedge is used to indicate a bond projecting out of the plane of the paper. Out of the plane of the paper means towards the observer, and dashed wedge is used to indicate a bond projecting out of the plane. This is also out of the plane but away from the observer. So dashed wedge will be away from the observer but out of the plane. Solid wedge will also be out of the plane, but that is towards the observer. Wedges are shown in such a way, this is also important point, such a way that broad end of the wedge is towards the observer. So broad end of the wedge is towards the observer, this end is towards the observer. So for this CH bond, which is towards the observer, the broad end will be at the hydrogen atom, and this bond which is away from the observer, this broad end should be at the carbon atom. The bond lying in the plane of the paper are depicted by using normal lines, and these normal lines, these two normal lines indicate these bonds are on the plane of the paper. And even sometimes it becomes difficult using even this wedge structure to understand the three-dimensional structure of molecules, organic molecules. In such a case, people use molecular models. And even if you use molecular models, whatever I have explained for this methane molecules, the wedge structure, and to show the three-dimensional representation, if you have a model, you can understand it in a much better way. Which bond should be the solid ways and which bond should be the dashed ways, shown in the form of dashed ways. Those things one can very easily understand, and then one can imagine also later on. Once you realize it's a structure, three-dimensional structure. So molecular models have been used to understand the three-dimensional structure of organic compounds, and the three most famous molecular models are framework model, ball and stick model. Ball and stick model is even the out, and then space filling model. Out of these three, ball and stick model is more commonly used all over the world. So this is most famous, and people can understand this thing in more easier way, because there one can also understand the atoms, different atoms, type of different uh, different elements, their atoms, something one understand, and there will be one places to put all the bonds so that they can be realistic with one another. This is a space filling model. These kind of things I think I have explained earlier as well. May not be the framework model, but ball and stick model and space filling model I have explained earlier as well in some of the classes. So what do we see? The molecular models are physical devices. They are physical devices that are used for a better visualization of three-dimensional shape of organic molecules. So to understand the three-dimensional shape of organic molecules, some physical devices we use, some beads we use, sometimes we also use some lines, some bonds, the sticks that represent bonds, and to understand the overall structure, three-dimensional structure of organic compounds. They are made of wood, plastic or metals and are commercially available. So these models they use either woods or plastic or metals, and they are commercially available. One can order even online these models. So generally three types of molecular models are used. So these are framework model, this is framework model, ball and stick model, and a space filling model. Out of three, as I said, this is more famous, more commonly used. So in the framework model, only the bonds connecting the atoms of molecules and not the atoms themselves are shown. And you can see here the atoms are not shown, only the bonds. So then these bonds are shown with the sticks, so different sticks, and each stick is made up of two different colors. And based on those colors, one can understand what atom can be there. Like here, one can see all there are four sticks, and these four sticks are joined together. Four sticks are joined together, and with the color, these blue color sticks are at the center. It means there must be one atom, one particular element which belongs to, and half of that bond belongs to that particular atom. And suppose it's a methane molecule, so this carbon atom and this carbon atom, four hydrogen atoms, different hydrogen atoms, and hydrogen atoms, their contribution towards the bond it is shown with the white color. And so this blue and white stick, it represents CH bonds. So there might be different color one can use for different bonds, and with that, using those representations, one can write, one can understand the three-dimensional structure of molecule, can make entire three-dimensional structure. Later, one can understand those structure as well. Now that these models, what we know that emphasizes the pattern of bonds, and it emphasizes only patterns of bonds of the molecule, and it ignores the atomic sizes, because in this bond, this representation, one may not understand what size of this carbon atom will be and what size these hydrogen atoms will be. So this their relative sizes also are not shown in these models. So these models only show the bonding pattern, like the structural formula that we write, and it may not show the actual atomic sizes of different elements and the atoms of different elements. In the ball and stick model, the ball represents atoms and stick represents bonds. Like here, these are all sticks. So sticks or the in the framework model. The different sticks will show different bonds, and the beads or the balls will show the different atoms or atoms of different elements. These balls are of different size, different colors, and based on that one can choose one color, one size bond uh, ball for one element, and different elements then we can join together with sticks to represent the structural formula of organic compounds. So in the ball and stick model, both the atoms and bonds are shown. So atoms are also shown, bonds are also shown. Balls represents atom and stick represents bonds. In this case also the relative atomic sizes are not taken care into the account. Like this hydrogen atom, what will be the relative size, exact relative size of this carbon atom and this hydrogen atom? It may not be shown appropriately in bond and stick model. And in reality, what happens? There is no such sticks in the chemical molecules. So this is, we do not see such sticks. What we see in reality that different atoms are they joined together, and their atomic orbitals and no even not atomic orbitals in the molecular orbital theory. Molecular orbitals they overlap with each other, and in that overlapping, what we see the atoms are there, and there will be certain overlapping, certain portions of these different atoms overlap, and so the real representation is a space filling model. But in the space filling models, we may not have the clear understanding of what will be the double, whether there will be double or single bond between different atoms. So to show that the ball and stick model, it also shows the understanding of the different bonds, double bond or single bond. Like for example, the compound C double bond C, the ethene, one can also use double stick to between two carbon atoms to show double bonds. And we also know that these sticks, these bonds, they are stretchable. There will be certain motion between different bonds. And if you go in higher studies, you will see this IR spectrum and all this kind of IR states that we see. So these bonds actually can be what we represented is using springs rather than sticks. So this, if you use springs instead of sticks, so such models will also called ball and stick and spring model. So compound containing C double bond C like ethene can also be represented by using springs in place of sticks. So in place of sticks, one may also use springs because these bonds are not rigid bonds. These bonds, their bond angles also, there will be vibration in the molecules, and those vibrations is what the bond length, there will be some oscillations of the bonds, and these oscillations, it changes the bond length, bond angle, and different oscillations are there and this, and that is why, and this oscillation will be the rigid bonds, one may not see those kind of oscillations. So one may represent those bonds with, once if people instead of springs instead of sticks, if you use springs, and so one can also use ball and spring model and ball and string model. However, but if the model, your model of your organic molecule is larger, so springs will have flexibility, so it will not keep the structure rigid to that particular shape or particular geometry. So we springs because of the flexibility, so it becomes difficult. You will have to have very rigid springs so to so represent the bonds, and there will be only slight oscillation that happens between bonds, and that we see because of the different vibrational levels, that whatever the energy the molecules if absorb, it may go to higher vibrational levels, and those kind of things that we usually see. So the space filling model now, the space filling model emphasizes the relative size of each atom based on its van der Waals radii. So the van der Waals radii of each atom is taken care in when one use this space filling model, and space filling model, the van der Waals radii, whatever the van der Waals radii, and there will be certain ratio that one use, because what we know the van der Waals radii will be in the youngest form, and the models that we use, these models we can see from our naked eyes. It means these models are much larger than those the van der Waals radii, real van der Waals radii. So real van der Waals radii we may not use, because if you use those, so there will be the atoms are already there, but we cannot see those atoms. So to represent that in the same ratio in the van der Waals radius, whatever the different atoms or different elements are there, in the same atomic size, atomic radius, we use of the van der Waals radii, we use different atoms, and these atoms are actually, there will be holes, and these different atoms can fit there together to show the space filling model. So a space filling model will give us the volume, molecular volume real molecular volume, the sense of the molecular volume of the molecule. So with that, not only that, we can, it will also give us the idea of the surface of the molecule, whether what kind of surface this molecule will have. And even with that surface, one can also find out the surface area. So this, to find out the surface area and molecular volume, one has to, and to get idea about the these things, molecular volume and the surface area of the molecule, one have to go to the space filling model. So in this space filling model, bonds are not shown in this, and bonds are not shown means if there is a double bond between two atoms or triple bond between two atoms or a single bond between two atoms, those informations will be not there, because in this space filling model we may not have to, we may not see those bonds, but it conveys the volume occupied by each atom in the molecule and so overall molecular volume as well. So in addition to these models, we also now use computer graphics to show molecule and for the molecular modeling and to show the molecular structure or three-dimensional structure of molecules. There are many softwares that visualization softwares one can use. There is a Modeling software, Chemcraft is there, Gauss View is there, VMD is there. Since there are many softwares, Avogadro, a number of softwares are there where you can use molecular graphics to really make, you can make the structure, three-dimensional structure of molecule. I can really have the real feeling how this molecule will look like in a reality, and so one can use those softwares as well. As I said, many softwares are there. For example, Avogadro, one name, Molden, another VMD, and then one can use Gauss View, Chemcraft, five softwares I have seen. Yeah, and most of these softwares are available free of cost. One can download those softwares in their computer and then you can open, make the structure and see, get the real feeling of those organic compounds. Now let us see the classification of organic compounds. The classification means what we know, there are in numbers, enormous number, a vast number of organic compounds are known to human beings. And there are still few new organic compounds are being synthesized or being discovered as well. So from natural products. So every day, every year, new and hundreds of new organic and thousands of new organic compounds are coming into the existence, that are being discovered or being synthesized, and there are already vast number of organic compounds. So how will we actually know even the basic understanding of those organic compounds? So to have certain basic understanding of all the compounds, what do? We classify these compounds into different classes. The similar thing was required for the periodic table, because there were new elements were discovered and each element has different properties. So how will one cannot have understanding of all the, one cannot remember all the properties of all the elements. Then we try to have certain kind of certain orders in, or maybe periodicity in their properties. And a similar thing one can do, based on that we prepared the periodic table. Now the similar properties may be the best kind of things we looked to classify organic compounds. And to classify these organic compounds, what we see, the structure function relationship or structure property relationship. So if the molecular structure is similar or the same, what we see, their properties will also be similar or same. And based on that, then people try to look into different structures, or maybe the structure, the prime structure of different organic compounds. And then we find out certain functional groups, certain portion of the molecule is there. That portion, that part of the molecule actually defines most of its chemical properties and some of the physical properties as well. So those properties, then we define that those portion of the molecule as functional groups. And functional groups, what is a functional group? And as you see, the functional group, it defines the function of the molecule, and though it's there in the form of a structure. So what do we do? So the most property used to classify organic compounds is the most common property is their structure, because we see based on the structure, structure is there, different molecules, different structure, different functions, the structure function relationship is there, the structure property relationship is there. So this structure we use as a function to classify different organic molecules or the organic compounds. So the organic compounds, first we divide this organic compounds into two parts. One is alicyclic or open chain compounds. These compounds are also called aliphatic compounds. Acyclic or open chain compounds or aliphatic compounds. Acyclic compounds, acyclic means there is no cycle, no ring structure. It has the same meaning when one write open chain compounds. So they have the same. These chains are open, they are not close together. If they will be close, so they will form a ring, they will form a cyclic structure. So these cyclic structures are not there. And the same thing we also call the aliphatic compounds. Then another class will be the cyclic or closed chain or ring compounds. So these compounds are there cyclic. They are not the two chains. If suppose one carbon chain is there and there is one single chain, and this chain, two ends of these chains are joined together through a chemical bond, carbon carbon bond is there, so it will form a cycle or ring, so or it will be a closed chain. So one can call such compounds as cyclic or closed chain compounds or ring compounds. Ring compound doesn't mean this compound will be the circle of the circular shape. It means this chain or two carbon chains are closed. If the carbon chain has branch chains, because acyclic open chain compounds, it may have a single chain or it may have different branches. So these branched compounds are also there, or single chain compounds are also there in acyclic or open chain compounds. And these compounds they may be hydrocarbons. Hydrocarbons is compounds containing only carbon and hydrogen. The example we know paraffin, all the alkanes, only carbon hydrogen there, and there will be saturation, there will be only single bond between carbon atoms. So that will be called paraffin. And then the olefins we know they are examples of alkenes, and there will be a double bond between two carbon atoms. The alkenes, then they might also have carbon carbon triple bond like the acetylene example that we have seen earlier. These are open chain or acyclic compound. A cyclic compounds, we know that these compounds will have a ring structure, their chains will be closed, they form a cycle, and these cyclic compounds can be of two types. One is alicyclic compounds, one class is called alicyclic compounds. Alicyclic means aliphatic cyclic. Though it is a cyclic compound, but its property will be similar to that of the aliphatic compound. So properties will be similar to that. It and there will be aromatic compounds. Aromatic compounds are a special kind of compounds, and we get that aromaticity and other things. What is the aromaticity? How a molecule gains aromaticity, and from the aromaticity, what advantages this compound will have? Those things we will see much later. You should just understand there will be these cyclic compounds may be of alicyclic type or aromatic type. The alicyclic compound will be the closed chain compound, but it will not be aromatic. Not be aromatic means this compound will not be planar. The entire compound is compound. If it is planar, the cyclic and some another formula is property there, the Hockel rule and this kind of things, then one can say this compound is aromatic compound. So it doesn't follow any of these three criteria. If it is not there, but the compound is cyclic, then one can put that compound into the alicyclic compounds. And the alicyclic means the compound, like if you look at the cyclohexane, these hydrogen atoms at each carbon atom, they are out of the plane. So these compounds are not a planar compound. So alicyclic compounds. So cyclohexane, it will have a chair form, which is more stable. So anyway, so those things we will see later. So alicyclic compounds can be of two types. One is called homocyclic or carbocyclic compounds. Carbocyclic means the cycle, each corner of that cycle carbon atoms will be there, and that is if the carbon atom, the same type of atom is there, and then the hydrogen atoms will be attached to those carbon atoms, then such compounds is also called homocyclic, because in that cyclic only one type of atom is there. And so this is called homocyclic or carbocyclic compounds. As I have said earlier, these carbon compounds may also contain heteroatoms, means other than carbon and hydrogen, there may be some other atoms between nitrogen, oxygen, sulfur, and so on. So the such compounds we call heterocyclic compounds. These acyclic open chain compounds may also contain heteroatoms. You should remember. So the heterocyclic compounds will win, and these are non-aromatic heterocyclic compounds, because aromatic heterocyclic compounds may be aromatic type as well. So those aromatic compounds will be different, that we will see later. So aromatic compounds, then another part of this cyclic or closed compounds. This cyclic or closed compounds could be aromatic compounds as well. And aromatic compound means the compounds having properties similar to that of benzene, or the structure similar to that of benzene. That is one of the very classic example of aromatic compound is benzene, and you should remember whatever the structure the benzene has, the similar structure if different compounds will have, then those compounds will be aromatic compounds. And in fine details we will see later on. So aromatic compounds, there could be aromatic compounds, could be benzenoid type, means these compounds contain benzene ring or non-benzenoid compounds, or these compounds even if benzene has all the at all the carbon corners of benzene there is a carbon atom, and but there could be non-benzenoid type and the heterocyclic aromatic compounds as well. The heterocyclic aromatic compound will compounds containing heteroatoms other than benzene, other than carbon and hydrogen. So the heteroatoms is aromatic compounds may have heteroatoms, so that will be called heterocyclic aromatic compounds. Benzenoid compounds, benzenoid aromatic compounds, non-benzenoid aromatic compounds, and heterocyclic aromatic compounds. Similarly, alicyclic means aliphatic cyclic compounds will be, they can be homocyclic or carbocyclic. Carbocyclic means the carbon is there, homo is the same, and the heterocyclic compounds. This could be the heterocyclic compounds other than carbon. Some other atoms will be there, and the corners or the each or the different centers of, or maybe one or two or more than one or two centers of the ring. So this, let's see the all of these classes one by one. So for let us first see acyclic or open chain compounds. These are also called aliphatic compounds. So acyclic or open chain compounds are aliphatic compounds. The acyclic compounds contain open chain of carbon atoms in their molecules. These open chains could be branched or the straight chain. So these carbon chains may be either a straight chain or branched chain. For example, we see the straight chain compounds, this N-butane, CH3, CH2, CH2, CH3. These are a straight chain compound, or but2ene or 2-butene. So CH3, CH double bond, CH, CH3. So these compounds may have single bond, double bond, or triple bond between carbon atoms, or they may also contain heteroatoms in this chain. For example, if you look at the acetaldehyde, this is also not a chain compound, or maybe at this end CH, this could be CH3, CH2, CH2, CH2OH. This example we have seen here, this compound. This compound is also a alicyclic compound or aliphatic compound, and it contains a heteroatom here. So but2ene, examples of branched chain compounds. So these compounds can be branched chain. So what if this CH3 group I can bring here at this position as well. So there will be migration. This CH3 group will migrate here. The hydrogen from here, one hydrogen will go here to complete the valency of this CH2 group. So this isobutane, this is called N-butane. This is called isobutane. Isobutane, we see there is a branch at the second carbon. First, second, and third. The second carbon, there is one CH3 group. This is a branch chain compound. Neopentane. This neopentane is also a branch chain compound. One can also have isopentane. And isopentane will be what? CH3, CH3, CH2, then CH3. So those compounds are I'm sorry, such compounds are branch chain compounds. And these compounds can also have, as I said, the heteroatoms and this acetaldehyde. CH3 CHO group. CH3 CHO group is what? It's also a open chain compound. And CHO group or CHA group, one can write as C double bond O and H. This is actually CH3 CHO. This is acetaldehyde. This is also an acyclic or open chain compound or aliphatic compound. Similarly, acetic acid, propionic acid, acetaldehyde, it is the propanaldehyde. So one can write that many n number of compounds will be there. They are all acyclic or open chain compounds. And this acyclic or open chain compound, as we said, based on the functional group, this is another one functional group, this is another functional group. Double bond is there, that is another functional group, and there is no double bond, it means it is a different class of compound. So there could be many type of compounds as well based on the functional grouping. Now let us look into the cyclic or closed chain or ring compounds. So cyclic compounds, and if you just join these two ends, together, so it will form a ring compound or cyclic compound. And a similar thing one can see. And even if the propane is there, that if these two ends, if I can join, if this is not there, so I can find this cyclopropane. So this is a homocyclic or carbocyclic compounds. Only carbon atoms are there at each corner or each points of the ring. So this carbon atoms will be there with the hydrogen, because the valency should tetravalency of carbon should be completed. So that is there. So these are all carbocyclic compound or homocyclic compound. This is cyclohexene. Cyclohexene is also a carbocyclic or homocyclic compound, because only carbon atoms are there in the each corner of this molecule. And even though there is a double bond in this molecule, the double bond may not define it is whether it is homocyclic or heterocyclic. It is the carbon atoms, the presence of carbon atoms or heteroatoms that defines whether it will be homocyclic or heterocyclic. And these compounds, we know the alicyclic compounds or aliphatic, these alicyclic compounds are also called aliphatic cyclic compounds, because we know in the aliphatic compounds the similar, although all if those aliphatic compounds comes into the cyclic form, so they are aliphatic cyclic or alicyclic compounds. And those aliphatic compounds we have seen, they can have double bond and they can also have triple bonds. But when the ring structure, triple bond is very difficult, because when in the ring structure there should be a certain angle, then only the ring will be formed. And if the triple bond is there in the ring, that angle, this angle will be less than 180 degrees, there will be a strain, so such molecules will not be stable. So sometimes atoms other than carbon are also present in the ring or heterocyclic compound. And this is called the, if the different atoms are present in the ring, they will call the heterocyclic compound. And this the example is tetrahydrofuran. The tetrahydrofuran is what? This is the heterocyclic compounds and heterocyclic alicyclic compounds or alicyclic heterocyclic. This is tetrahydrofuran, the piperidine. There may be another examples if this is the tetrahydro. Pyrrole is also example. There are n number of examples. One can put piperidine. One can have two NH groups, one NH group here, one NH group here. Similarly, one can have O and here N or O. There are many compounds one can have. These are all heterocyclic compounds, and the heterocyclic compounds which are not aromatic. So non-aromatic heterocyclic compounds. These are non-aromatic heterocyclic compounds, and it is here written non-aromatic heterocyclic compounds. And if the heterocyclic compounds are aromatic, then we will call aromatic heterocyclic compounds. So these compounds exhibit some of the properties similar to those of aliphatic compounds, and so they will be they are called alicyclic or aliphatic cyclic compounds. Let's now see aromatic compounds. So aromatic compounds are a special type of compounds, and this special type of compounds means they have different special kind of properties, and this special kind of property is molecular. Because of that, is the chemical the chemical properties and also some physical properties of these compounds are different. And because of which these molecules aromaticity, one kind of a stability term one can understand. Because of this aromaticity, these compounds are very stable compounds, and because of this stability, these compounds are less reactive, and that less reactivity even during some reaction happens in the chemical reactivity, because these compounds have this pi bond, and this pi bond means the electron density is more at this at the above the planes. So these compounds may have this kind of reactions, but what we do usually we see, since aromaticity should not be disturbed, these molecules mostly show the substitution reactions, and those things in details we'll see later on. So the aromatic compounds are a special type of compounds which include benzene and other related compounds. And other related compounds, so these compounds are called benzene-wide compounds. So aromatic compounds could be benzene-wide aromatic compounds or non-benzene-wide aromatic compounds or heterocyclic aromatic compounds that we have seen. The benzene-wide aromatic compounds are what the benzene base. So this is benzene. So similarly, NH2 group is attached here, aniline. One can have OH group, the phenol, this benzene ring, and one OH group phenol, one CH3 group toluene, mesitine. There are many examples, and two C benzene rings fused together. The naphthalene, similarly, one can have anthracene, phenanthroline, the three benzene rings fused together in one line. So that will be anthracene. If another third benzene ring will be here, then that will be phenanthroline. So there are many fused rings. So these compounds, aromatic compounds, they are all aromatic compounds. They are called benzenoid aromatic compounds. Means this compound, the major structure is the benzene. Aromaticity has come because of the benzene ring that is there in the molecule. And then the non-benzenoid aromatic compound, the example is propone. You may not understand how these classifications are based on all the molecules, how one can define the whether this molecule is aromatic or non-aromatic, or the aromatic cyclic or non-aromatic cyclic or alicyclic compounds. We will see what are the definitions of aromaticity. Based on that, one may recognize whether this compound will be the aromatic compound or non-aromatic compound, even if it is a cyclic compound. So, few of the properties I may say: the compound should be cyclic, compound should be in a plane. Two things, and third thing is all these double bonds should be on the alternate position. So, there will be conjugation that we call. Conjugation means these pi bonds that are there in the compound, they should be completely delocalized. So, in this compound, what we see with this pi bonds, they are in the conjugation, and this p orbitals with one electron is here. This is one electron. This is one electron. So in this case, there is a pi bond, p pi bond here. But that p pi bond may happen between these two atoms as well. So in another case, what will happen? This p pi orbital will overlap with this p pi orbital, and so this bond will be broken. So this p pi will now overlap with this, and there could be many such overlap. And with that, there will be many possible structure of this compound that we call compound the conjugation. So those conjugation based on the possibility of the delocalization of the double bond, we call conjugation. Here also there is such possibility, although this p pi bond is here. So this carbon atom is also involved in p pi bonding with this oxygen atom. So if that oxygen, this p pi bond broken, so this p pi orbital will be there, and that orbital may overlap with this one. So there will be conjugation, a complete conjugation here as well. And the next point is the Huckel rule. That Huckel rule we will see later. So the complete conjugation should be there. Molecules should be planar, and we see these molecules are planar, and the cyclic structure. Then there will be aromaticity. And these aromatic compounds could be the heteroaromatic as well. The heteroaromatic means what? Other than carbon atoms, there will be some heteroatoms as well. And the heteroatoms, you know what are the heteroatoms? The highly electronegative atoms, and the highly electronegative atoms will be on the right top of the periodic table. They could be nitrogen, phosphorus, oxygen, sulfur, or maybe entire halogen group. So fluorine, chlorine, bromine, iodine. So these are the heteroatoms that are usually exist in aromatic compounds. Now let's see into the functional groups. As I said, different groups, even in whatever the classifications we have made, we can also see even in this classification, the alicyclic compounds or open chain compounds, there will be in different types of compounds, and those compounds are based on the functional group that is there in that compound. And the what means, what is the functional group? If you look at this compound, C double bond O, and this H is here at C double bond O and OH, and CH3 is same, and this compound. So these all these compounds, they have different physical and chemical properties, and based on, because there have different physical and chemical properties, everything is different, so their use is different for us. So what actually determines the physical and chemical properties of different molecules? So that part, whatever that a smaller part, the structural part of the molecule that is there, and which determines its chemical properties and physical property, that we call functional group. So this CH3CHO. I may write this CH3CH2CHO. We do not see much difference in the physical and chemical properties of HCHO or CH3CHO or CH3CH2CHO. So this property, then what does it mean? Means the CHO group is actually determining the chemical and mostly chemical properties of this compound in this case. So one may call this as a one functional group. Similarly, there is not much difference in the chemical properties of CH3COOH or HCOOH or CH3CH2COOH or CH3CH2CH2COOH. It means there is not much difference in the chemical properties of all these compounds. But even if just one change of this oxygen atom, these properties are completely different. It means whatever the structural unit that is there and which is determining the chemical properties of this compound are called the functional group. So this functional group, so let's see what is the functional group and what is its definition. So a functional group is an atom or a group of atoms joined to the carbon chain of an organic compound, and what we see, all these groups were joined to the carbon chain. See this carbon chain, and there may be one atom or the group of atoms. So earlier what we see, this OH group here, we have seen this OH group as well. This is also a functional group. This Cl, this is one atom. This is also a functional group. So one atom, it may be one atom or the group of atoms which are joined to the carbon chain of the organic compound and is responsible for its characteristic chemical properties. And that is why, because this particular the heteroatom that is attached there and this atom or the group of atoms, it determines the chemical characteristic chemical properties of that entire organic molecule or organic compound. Then that group is called the functional group. And the functional group, usually what we see, functional group usually either it will be double bond or a triple bond, or maybe the heteroatom or heteroatom. So whatever the group the heteroatom is associated to, that we call the structurally, one can call that as a functional group. The examples of the functional groups are hydroxyl group that we see. Hydroxyl OH group is the hydroxyl group, which means this is alcohol is the functional group. In this case, we call it as alcohol. Amine group, you know, NH2 or this NH2 hydrogen atoms may be replaced with different alkyl chains. So this is a primary, secondary, tertiary amine. Then maybe the aldehyde group we have just seen, C double bond O and then H, that is aldehyde group. CHO group. Then the carboxylic acid group that we have also seen, this this is aldehyde group, and this is the carboxylic acid group, COOH. So this we call COOH, the C double O H. These are carboxylic acid group, and these are the functional groups. There are many functional groups that are there in organic compounds. We will see what are the general common functional groups that is there with the organic compounds. What do we see? There are compounds, organic compounds, where more than one functional group is linked to that organic compound or is present in that organic compound. When more than one or functional group is present in one organic compound, then such compounds are called polyfunctional compounds. Means more than one functional group is there, so such compounds are polyfunctional compounds. So what will be the chemical, which functional group will determine the chemical property of that compound. So it depends on which functional group is more reactive, because functional groups are what? These are the reactive part of the molecules. And if that molecule, this compound is there, so that reactive part, that the functional group will mostly react into, take part into the chemical reaction. And that is why I said if the CH3, CH2, COOH or CH3, COOH or HCOOH, only COOH group will mostly take part in all the reactions, chemical reactions. So it will determine chemical properties. CH3 group, it may modulate some of the properties or modify some this chemical properties slightly a little bit, but the chemical properties, the chemical reaction will happen on COOH group, so it will determine the chemical property. Similarly, if there are more than one functional groups on one compound, that means the polyfunctional compounds are there, means then we will see which of the functional group is more reactive, and whichever the functional group is more reactive, that functional group will take part into the chemical reaction. And so even if in the society, what we know, if there are more than one people, the person and some work is there, the person who is more active, he will do the work first. So similar thing happens there as well in the organic compound. The functional group which is more reactive, and usually we have seen in all the cases they are more reactive. And even how will we know they're more reactive? If the different organic functional groups are giving same chemical, undergoing same chemical change or same chemical reaction, then we'll see which functional group will give the faster reaction. Or if the more than one functional group is there on the compound, we'll see which one is reacting fast. And whichever is reacting first, based on that we have also defined people have defined the priority of this functional group, the preferences, in which preferential order they do chemical reactions, and those orders that we will see a bit later on. So before that, let's see the homologous series. So belonging to each functional group, as I said, CH3, CH2, COOH, CH3, COOH, HCOOH. If you remember, if you focus on this, or maybe look at this structure of these different compounds closely, you will see there is difference of one CH2 group in each of the compound. CH3, CH2, COOH. Now, if I the middle CH2, if I remove, it will become CH3 COOH. Now, if the terminal CH3, if I remove CH2, it will become H hydrogen only, a COOH. Then the difference of one CH2 group is there, and if this similar series you find for one functional group, one type of compound, this kind of series we called homologous series. Homologous series. So a group of or a series of organic compounds, each containing a characteristic functional group, forms a homologous series. So it has a characteristic functional group will form one homologous series, and members of each homologous series are called homologs. So members of one homologous series will call homolog, and one homologous series will have similar chemical properties. Um, so there are a number of homologous series of organic compound, and some of these are alkanes. So alkane will have one homologous series. So you know methane, ethane, propane, butane, pentane. So they will all have difference of one CH2, CH2. Keep adding CH2, CH2 groups, and you will find different alkanes. The alkanes, similarly, alkenes means the ethenes, example is ethene. Alkynes, alkanes are the or hydrocarbons in which all the carbon-carbon bonds has a single bond, and all the carbon-carbon bond contains a single carbon-carbon bond. Alkenes have carbon-carbon double bond. Alkynes have carbon-carbon triple bond. At least one carbon-carbon triple bond is there, then we call that such functional group alkynes. And if at least one double bond is there, then we call such compound as alkenes. And if there is no double or triple bond, and double bond means alkenes, so at least one double bond between carbon carbon and alkenes. Again, repeating one at least one carbon carbon triple bond alkynes. So ines means triple bond, ins means double bond, and anes alkanes. The anes means carbon carbon single bond only. Then haloalkanes we have seen the this chlorocarbon earlier. So this haloalkanes means the organic compounds. The alkanes usually if the alkanes or hydrocarbons have halogen atom. So it may be chlorine, fluorine, bromine, or iodine. So that such compounds are called haloalkanes. So haloalkanes will have one homologous series. If the fluorine is there, one homologous series. Chlorine is there, one another homologous series. Bromine is there, another homologous series. If iodine is there, it will be another homologous series. If one chlorine is there, one homologous series. If two chlorine is there, there will be another homologous series. So based on their numbers, one can also define different homologous series. Then alkanols are what? Alcohols. Then alkanals are what? Alcohols. The example we have seen here, alkanols. This compound is alkanol. Actually, it is alkene and then alkenol one can say. So it's kind of alkanol. Then this the is the haloalkane. This is haloalkane, the chloroalkane, the chlorocyclohexane, because this is hexane, 6 groups, and the cyclohexane, which is a cyclic compound, so cyclohexane, and it has a chlorine, so chlorocyclohexane. So then this example we have also seen this al, this aldehyde group, the alkanals. This is alkanoic acid, the so alkanones. These are ketones, alkanals, they are aldehydes, alkanoic acid, they are carboxylic acid, amines, etc. They all can have a different homologous series. The members of a homologous series can be represented by general molecular formula. So each homologous series can have one general molecular formula, and one can define the general molecular formula. For example, alkanes. We know the general formula for alkane is CnH2n plus 2. If it is alkane, so it will have a general formula CnH2n plus 2. And if you just change value of n from 1, 2, 3, this is one integral value. You can keep changing the value of n and keep getting new organic compounds, new alkanes. So similar to that, all the homologous series will have one common general formula, one common formula or general formula, and the successive members, each successive member of this homologous series differ from each other in molecular formula by CH2 unit. So one member, successive members, that they have difference of one CH2 group. If the difference of two CH2 group will be there in the on the alternate members. So this is what one, based on that one can find out these things. And let's now see what are the different functional groups and general functional groups. We'll see these functional groups. They are very important thing. Until unless you do not understand the structure of different functional groups, you will not understand organic chemistry. So we will have to remember this table as well. So classes of compounds and the functional group structure we will see, and then IUPAC prefix. These things we will see maybe later on when we will see the IUPAC nomenclature of organic compound, and the examples we will also see of the different class of compounds. So alkanes, we know the more general compounds, and the alkanes, they will be their saturated compounds. There is only carbon and hydrogen, and each carbon has only single carbon carbon bond. Such compounds are alkanes. They are paraffins. They are also called paraffins that we know. The example is butane, pentane. We have seen earlier, like here. These are all alkanes. Although they are cycloalkanes, this alkane, this is also cycloalkane. These two, these are alkanes, isobutane, neopentane. This N-butane is also alkane. So these are all alkanes. If the double bond is there, it is not alkane. This is alkene. So alkanes, then alkenes will have the functional group C double bond C. So this functional group C double bond C is there. So if it is more reactive than CH group or CC double single bond, so that's why it defines the chemical property of a compound. And this such functional group, if it is there, carbon carbon double bond, we call alkenes. And the example is butene. One can see other examples. One can also see these are not alkenes. These are aromatic compounds. So alkene, this is cyclohexene, this is alkene, this is also alkene, but2-ene. So the alkenes, the but1-ene is shown here. So this is alkene, then alkyne. Alkyne means carbon-carbon triple bond. This is the functional group. Alkynes. So ines, ine means you see triple bond, ene, double bond, ane, single bond is there, carbon-carbon single bond. The example is ethene we have seen, then but1-ine. Now ethine or acetylene is one example of alkynes, and this but1-ine is another example. So this is also alkynes. Then arenes. Arenes are what? Arenes are, they are all aromatic compounds. The benzene example. So this is a class of compound. Arenes are also called. These are aromatic compounds. So this aromatic compound like butane, they are basic or aromatic compounds. Then halides. If the aromatic compound it has halide, so however, this class of compounds will have halides, so they can be called haloalkanes. For the halides, they have halides, and halides means the X group is there. X may be fluorine, chlorine, bromine, or iodine, which is associated to the carbon atoms, and this we call with the haloalkanes. The halides are also called haloalkanes. One example we have seen the chlorocyclohexane. Here it is one bromobutane and one bromobutane. We can see here. The bromo group is at the first one carbon atom, and why, how this name came, we'll see in IUPAC nomenclature. I'll explain these names once again later on. So this compound, you can just see the structure of this compound. This halide is there. Halide means a bromine is there, a bromide is there, and this organic compound. So this is called the haloalkane, or this is the bromoalkane. Halo means the bromine. If bromine is there, bromo, chlorine is fluoro, chlorine is chloro, iodine iodo. Then another group is called alcohols. If OH group is associated to the carbon chain or carbon ring at any point, then such compounds are called alcohols. And then you see CH3, CH2, CHOH, CH3. This OH group is here, it is associated linked to this CH group. If this OH group may be linked to any of the carbon atoms at any of the positions. So anywhere if this OH group is there, then such compounds are called alcohols. Anywhere this bromine is there, then it is called halide. This bromine can be on this carbon. This bromine can be on this carbon as well. This carbon, same carbon. So that those things we'll see. Then the aldehydes. Aldehydes have CHO group, and CHO group as a functional group. And this CHO group means what? If you know the how to write the structural formula, you can write the structure of this CHO group as well. This CHO group we are showing one dash to this carbon, means this carbon is, there is some group that is associated to this carbon, and this is the carbon chain where this CHO group is attached. This is showing means there is a carbon chain. This line is showing means this X is attached to one carbon chain. So this, whatever the bond that is shown, it means it is some carbon chain is associated or linked to this group. The OH group is linked to one carbon. That is why with the one dash line we are showing here. This CHO means one carbon-carbon bond is already there. Then one hydrogen is there, so carbon-hydrogen single bond. Two bonds are there, and two more bonds for this carbon is required because carbon is tetravalency. It means the carbon must have a double bond with this oxygen. Then only we also understand that octet of oxygen will be complete. So it is nothing but C double bond O and then CH. And this is also called formyl group or oxo group. Formyl, formyl or oxo, these things you should remember. And the functional group in IUPAC nomenclature we write as hull. If it is as a side chain, means if it, there is a polyfunctional compound and the aldehyde is there, and in that compound there is another functional group which is more reactive than aldehyde, then in writing the name of this aldehyde in such a case will call oxo group or formyl. Other than if the aldehyde is the primary functional group, then we call it as Al. And if this aldehyde group is not the primary functional group, it is behaving as a substituent, then it is called oxo or formyl. And similarly, what we see, this is also the halo, which is also the functional. This is a hydroxy. If it is not the main functional group, it is just as a side chain or maybe the substituent. And there is another functional group that is already there, which is more reactive than this alcohol. Then we call that alcohol as hydroxy. And if the hydroxy is the primary functional group, then we call such compounds with OL, all. All, this is all. And if this carbon atom is now, you see this hydrogen, instead of this hydrogen in the aldehyde group, there is another carbon chain. One carbon chain was already there, and now this hydrogen is replaced with another carbon chain. So two bonds, two, this is two bonds, this is not greater than sign, this is two bonds, means this carbon will have two different bonds with two different carbon atoms. When two different alkyl groups it is connected. So this is how we show two bonds which are not shown here, and then C double bond O is now this is called ketones. Such functional groups are called ketones. Means RCOR. These are called ketones. And if this ketone is the primary functional group, then it is called one. And if this ketone is not the primary functional group, some other more reactive functional group is there on the compound, then this is also called oxo group. Then the nitriles, you know, it is CN group, C triple bond N. This carbon will be associated to or linked to another carbon chain or the carbon atom, and the carbon chain or carbon atom. So this is called, if this is the primary functional group, we call it nitrile. And if this is not primary functional group, it is secondary functional group, and some more reactive functional group is there, we call it a cyano group. The example one can see here, the CH3, CH2, 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 CN. This CN could be here, this CN may belong to here. If it is on this carbon, it is the same. From here, instead of here, if you write the same compound will be there, it will just repetition, same compound, and this may be here, but this and this, they are the same position. So those things we will see same position. So only two different type of compounds can be formed with the CN. CN could be on the terminal carbon or maybe on the second carbon. The ketones examples, as I said, the two alkyl groups are on the associated to this carbon. An example you see here, CH2, CH3, CH2. One alkyl group that is associated to this carbon, and another alkyl group is CH3, and then there is C double bond O. CO it is shown, means it is C double bond O, because this carbon is connected to only two carbon atoms, and with these two carbon atoms and this both the carbon atoms, their tetravalency is getting completed if there is only single one. Like what does do I mean? Means this carbon has three valencies because of this hydrogen atom. Means this carbon requires only one valency, only one bond with this carbon atom. So there is only one bond. And this carbon atom, you see this carbon atom has one carbon single bond with this carbon, and two single bonds with two hydrogens. So three bonds. So only one bond is here. So there will be, this carbon is associated with a single bond with this carbon also has a single bond with this. So there is a carbon-carbon double bond to have the tetravalency of carbon completed. So this is on the ketone group, and the aldehyde group, the example one can see here, CH3, CH2, CH2, CHO. This is at the terminus. So at this CHO group, if the C double bond O group is at the terminal, So you need one hydrogen to complete the tetravalency of carbon. So such functional groups are called aldehyde. If this carbon COO group is not at the terminal of the carbon chain, it is in the middle of one long carbon chain, because these all are carbon. This one can count one carbon chain considering all of them. So this is called, then it is ketone group. One way to understand this. Then an trial example we have seen, and the ethers are what? The two alkyl chains are there and one oxygen atom is between two alkyl chains. So one oxygen, then this is called and this is called ether, and ethers, their name we write as something else. So these are ethers, and if these ethers are not primary functional group, if they are not primary functional group, then their name will be like they will call alkoxy. And what does this means? And again I'll say IUPAC nomenclature will see. So ethoxy, the example is what? Such compounds are CH3, CH2O, CH2, CH3. This O can be here as well. I can just put this oxygen here. So the other example will CH3, CH2, CH2O, CH3. So that will be another ether, another, and so another compound. So this compound O is here in the middle, the CH2, CH3, CH2, CH3, and the name will be like it is called ethoxyethane. So this O and one alkoxy we call it ethoxy, and one alkyl group we call it ethane. The how the name will come, we'll see later on. Then carboxylic acid. Carboxylic acid, at the end of the carbon chain, one C double bond O H group is just attached, and what we know here, this is one OH group and one carbon double bond O group. It is one C double bond O group and one OH group that is there. So two oxygen atoms, one oxygen atom attached as C double bond O like this, and one OH group like this is linked to this carbon atom. So this functional group we call the carboxylic acid, and the carboxylic acid, if it is the main functional group, usually it is the main functional group whenever it is an organic compound, it is most reactive or functional group. So we call the oic acid the name, and if it is there as a substituent, then we call it as a carboxy. And now if this carboxylic acid, if it removes, if this H plus is removed, and then there will be COO minus, this is charge on the COO group, this we call a carboxylate ion, and the carboxylate ion will be O8. We know it, we call O8. And whenever the carboxylate ion, it is very most reactive, usually we do not put it as a prefix. So esters, now esters are there. So if this hydrogen is replaced with this another alkyl group, here what we have seen, this hydrogen replaced with another alkyl group, so aldehyde becomes ketones. Similarly, if the carboxylic acid is there, this hydrogen is replaced with another alkyl group, because this carbon is already associated to another alkyl group. So this alkyl group and this hydrogen is another alkyl group. This then we call it as ester, and esters are also called O8. And if the esters are there as a less preferential functional group or less reactive functional group, then they will be called alkoxycarbonyl. These names you have to remember. And example one can see here: CH3, CH2, COOCH3. Now one can also write CH3, COO, CH2, CH3. So this CH2 one can move there. Then another will be H, COO, CH2, CH2, CH3. That will be another ester. Then acyl halide. Acyl halide will be COX. Now this OH group, one can replace OH group with one X group or the halo group or a halide group. This halide could be fluorine, chlorine, fluoride, chloride, bromide or iodide. So if one replaces this OH group of carboxylic acid with one halogen group, then we call such group as acyl halide, or acyl, if it is chloride, chlorine, this is acyl chloride, acyl bromide, acyl bromide, acyl iodide. And example you can see here: CH3, CH2, CH2, COCl, and this will also be at the terminus like all carboxylic acid groups. And amines, NH2, this is the primary amine. As I said, if you replace one hydrogen of ammonia, I will replace one hydrogen with one alkyl group, then it forms primary amine. If two hydrogens of ammonia you replace with two different alkyl groups, so two different alkyl groups, one or two, is associated to this NH group, then it is called secondary amine. If all the hydrogens of ammonia is replaced with three different alkyl groups, then we call such alkyls as tertiary, such amines as tertiary amine. They are all amines. So tertiary amine, there is one alkyl group here, one alkyl group with this bond, one alkyl group here. So all the three hydrogens of ammonia is replaced with three different alkyl groups. So they may be replaced with three same alkyl groups. So there's three alkyl groups, one can say three alkyl groups, then we call such amines as tertiary amine. So this is tertiary amine, this is secondary amine, this is primary amine. Only one hydrogen is replaced with one R group. So this is RNH2 or the alkyl group. We call it as a primary amine. They are all amine groups. So amine groups, they are amine groups, and this amine, when it is less functional part of the molecule and it is there, and means in that molecule there is another more reactive functional group is there, then we call such group as amino group, and this group will behave as a substituent. So the example you can see CH3CH NH2, CH2CH3. It means this is CH3CH, CH2CH3, and this NH2 group is there with this CH group. NH2 group as a here. CHNH2 here, and then CH2CH3. This group can be in between, so one can also write this CH3, CH2, NH, CH2, CH3. That will be secondary amine. Then one can also write CH3, CH2, N, CH3, then CH2, CH3. Then that will be tertiary amine. Or one can write nitrogen 1 CH3, 1 CH3, 1 CH3, all the three hydrogens of ammonia replaced with three different CH3 groups. That will also be a tertiary amine. Now let's look into the amides. The amide CO. Amides are what? If you just replace this X group with the NH2 group, or the OH group of carboxylic acid is more general OH group of the carboxylic acid with NH2 group, then such functional groups are called amide. So CONH2. Now, like the amines, amides can also be primary, secondary, or tertiary. So what we see, this is the primary amide. So primary amide means if the primary amine replaces the OH group, then we call primary amine. If the secondary amine replaces, means this is replaced with the NHR group. Like this NH group is there, NHR group is already attached, and one N group will be carbon nitrogen. So this is secondary amide, this is tertiary amide. That means one OH group is replaced with NH2, then this is primary amide. This CONH2 group is called amide group, and this butamide example is CH3CH2 twice CONH2. This what we CH3CH2 CH2 CONH2. This is primary amide. Then what can I do? I can put one CH3 group at that side. So CH3CH2 CONH CH3. Then that will be secondary amide. Then one I can also write CH3 CON CH3 CH3. That will be tertiary amide. So in the different R group means the alkyl group. One can see this R group here. R group is already there. This R group and this R group is up to here. CH3 CH2 CH2 R group. This, and so CONHR is just again if you remove primary amide from the primary amide one hydrogen and put one alkyl group, it is called secondary amide. And if both the hydrogens of the primary amide is replaced with two different alkyl groups, then we call tertiary amide. This is called tertiary amide. Then the nitro compounds are there. Nitro compounds will have functionality NO2. The structure will be there. These compounds are called nitro compounds. And this example CH3, CH2, 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 NO2. This NO2 group can be on the other carbons as well. Then the sulfonic acid SO3H. This sulfonic acid, it's the H2SO4. From H2SO4, you just replace one hydrogen. H2SO3. From H2SO3, you just replace one hydrogen with one alkyl group. Then such compounds are called sulfonic acid. And sulfonic acid, and the sulfonic acid is the primary functional group. If it is there as a secondary functional group, means the less reactive functional group, then it is called sulfo. group. And what we know that in the case of polyfunctional compounds, one of the functional group is chosen as the principal functional group, as I said, and the principal functional group is the functional group which will undergo chemical reaction first. So that will be the principal functional group. The remaining functional groups are subordinate functional groups, and these subordinate functional groups are also they behave as substituent. The subordinate functional group, the primary functional groups. So if the many functional groups are there in the organic compound, how will we know which group is the primary functional group? The choice of principal functional group of the primary functional group is made on the basis of following order of preference, and this order of preference we use, and this order of preference has been prepared based on the chemical properties of the organic compound. So this is COOH, the carboxylic acid, most reactive, and its reactivity. And then sulfonic acid. Then you see this is the ester group, COOH. You see here carboxylic acid, COOH. Then SO3H, sulfonic acid group. Then COOR, this COOR is ester. You should remember all this. The R is alkyl group. COCl, this is oil chloride or alkanoyl chloride or acyl halide. The oil halide, you see oil halide. Oil halide. So acyl halide. So acyl halide, COX. Then CONH2, amide group. The amide group. CONH2 or maybe the secondary or tertiary amide group. Then CN group, nitrile group. The nitrile functional group. The CN functional group. Then this aldehyde functional group. Then the aldehyde is this. And then comes the ketone. The ketone, it means the aldehyde is more reactive than ketone. And here also the carboxylic acid is more reactive than esters or even the acid halides or the amides. And then OH, after the ketone comes the alcohol group OH. OH is the alcohol functional group OH. Then comes the amine groups NH2 on the primary, then secondary and tertiary amine, and then comes the double bond. And double bond will be at the last, and rest of the other groups, the functional groups that we see, they are like of the substituent, they are kind of subordinate functional group. They behave as like this. So this order you should also remember: carboxylic acid, then sulfonic acid, then ester, then acid halides, or the acyl halide, one can also call it acyl halide, then amide, or the acyl halides we also call acid halide, or the amides, then nitrile, then aldehyde, then ketone, then alcohol, then amine, then alkanes. Now let's see this question. Which functional group is principal functional group in the following compound? What we see here, this compound CH3 C double bond O CH2 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 C double OH. We see two different functional groups. This is the carboxylic acid and the carboxylic acid we see here. If you don't remember, you can again see here C double OH. Carboxylic acid, another functional group is RCOR. So two alkyl groups attached to carbonyl group. This C double bond O is called carbonyl group. So two alkyl groups are attached to carbonyl group means C double bond O. It means it is ketone, like ketone. So this is, there is another one R group here, is another R group is ketone. And so two functional groups are there, ketone and the carboxylic acid. And what do we know? If you look at the order of preference or the priority of their reactivity, we see carboxylic acid group is more reactive than the ketone group, because ketone group comes later into the in the priority order. So carboxylic acid will be the primary functional group or the principal functional group, and this will be the subordinate functional group. So this compound will behave as if it is a carboxylic acid compound, or this is a carboxylic acid. So I'll stop here. I'll again explain this thing in the functional groups in the next class, and we'll move to the IUPAC nomenclature of organic compounds.